All right, so we are interested in describing an explicit implementation for HDiv conforming simplicial finite elements in MFEM. So a little overview, we're going to do some motivation, some mathematical preliminaries, going to go through the actual implementation details, and then show you some order of accuracy results. So motivation first. So why are we interested in these discretizations? Well, we look at this formulation of the homogeneous Maxwell's equations in 4 dimensions. And so what you'll see is that we need finite element spaces for our classical curl or divergence. Today, we are going to be focusing on just the HDiv conforming elements, however. And so our objective, again, was higher order conforming elements for Maxwell's equations. And the current problem is that the existing 4D branch in MFEM that seems to be developed mostly by Andreas, who I believe is in the call today, only focused on like lower order elements mostly. So we need to expand that. So if we jump into our mathematical preliminaries, we see a lot of our classical operators, derivative operators in 4D. We see our gradient, our curl, our divergence, but we also see the emergence of a new derivative operator, which is this skew grad. So we are able to form the infinite dimensional Sobolev spaces, whose construction guarantees boundedness with respect to the L2 inner product when applied to the derivative. The highlighted green box is the Sobolev space associated with our divergence operator. Furthermore, we can construct our finite dimensional subspaces from these infinite dimensional Sobolev spaces for each of our derivative operators. Again, the green box highlights the HDiv conforming elements, which are really just an extension of the Ravier-Tamá space, but in 4D. So our inspiration comes from a paper written by Fuentes et al., which focused on geometric elements across, or like all geometric elements in 3D. They were higher order, so it was really good framework. We continue we use the Fuentes approach because it has a very intuitive construction based on these barycentric coordinates. We can generalize it into higher dimensions. It's also very flexible, so we can use it for many different types of derivative operators without modifying it too much. These functions have a hierarchical structure, and as I think mentioned earlier today, we have an implementation in MFEM already for square pyramids in 3D by Mark. So we kind of have some precedent in that sense. And we extended, or Nigam and Williams extended this work to 4D simplices. And so they did that in this paper, again, focusing on the pentatope, which is the 4 simplex, and creating these discretizations. And so our HDiv conforming shape functions are displayed here. On the left, we have our bubble functions, which are associated with interior degrees of freedom on the pentatope. And then on the right, we have our tetrahedral facet functions for degrees of freedom on the tetrahedral facets of the 4 simplex. Each function is, or each set of functions is constructed using Legendre and Jacobi polynomials. So they have a very similar structure that plays into that hierarchical nature. So implementation details. So I think it's only natural first address the degrees of freedom. So each pentatope has 5 tetrahedral facets. And for a order equals 1 element, we have 5 different vector degrees of freedom for each tetrahedral facet. And then we have 4 co-located DOFs for this order element on the interior of the pentatope. These degrees of freedom are vector degrees of freedom, and the facet degrees of freedom have a outward-facing normal associated with each of them, and the interior degrees of freedom have vectors associated with them, which we prescribed as the coordinate directions. This choice isn't unique. You can use any four orthogonal vectors prescribed to the four co-located DOFs. And so we move towards constructing a Van der Waals matrix. So if you take your jth vector basis function, which has components 0 through 4, you evaluate this at some point. You can then contract each function with a normal vector as associated with the degree of freedom. And then this operation, this contraction operation returns a generalized Van der Waals matrix. So what does it mean when we talk about orientation matching across elements? So in 3 dimensions, we have 4 triangular faces on a tet, and these have 6 unique orientations that are produced by either reflections or rotations of a base geometry. So in 4D, we have 5 tetrahedral facets, and we need to match these orientations, which require us to compute 24 unique orientations, again, prescribed by this reflection or rotation. And so if we take a look at the 2-dimensional example, you have some identity configuration of degrees of freedom on a triangular face. You use reflections or rotations to produce different orientations. For HDiv, we actually have special consideration because we have this outward-facing normal. And when you do a reflection, the direction of that normal changes, so you have a sign flip in that vector. So we need to take special care to account for that. And we do this by basically constructing a array of orientation indices. So it's just different combinations. You'll see the 6 unique orientations. And then in order to encode the sign flip, we actually shift any orientation that is produced by a reflection. We shift those indices into the negative to account for that sign flip. And the snippet of code to the left is just like an example of that kind of procedure. It's all done at once. There's not 2 separate tables. It's just for clarity. We do the exact same thing for orientations when we're talking about our tetrahedral facets. These tables are abbreviated. There's 24 different orientations. But again, you just create your table of orientation indices, and then any orientation that is created by a reflection, you need to track that normal vector sign flip by shifting the degrees of freedom to the negative. And then so we move forward to our order of accuracy results. So we did just a simple extension of the grad div problem that's in the MFEM like suite of examples. I think it's example 3 or 4. We just prescribed some type of forcing function to create our analytical solution as follows. And then we see that we get p+1 accuracy up to order 4 polynomials. So it proves that our basis is functioning correctly. And then so for future work, we're going to be continuing to the HQ grad and the H curl conforming spaces on the 4 simplex. And all those theoretical details can be found in my advisor, Dr. David Williams' talk that he gave. Should be on the MFEM website in the seminar page. So yeah.
So thank you for letting me talk about my research today. So what we want to talk about is kind of a new method that I've been working on for about the last year. And this is specifically a method for solving advection equations, right, where you have incompressible flows. Okay, so big picture, we know that our velocity field should be incompressible, right? Maybe we're solving Navier-Stokes or something like this. But the advection scheme might result in something different, right? And this could be from, say, spatial error, could be from time integration, or error in the velocity field itself, right? For example, if we use an approximate projection method, right, our velocity field is not exactly divergence free. So say, okay, if we can use this idea, can we make a more robust advection scheme? So this is what we're working on. So the base of what we're doing is using the semi-Lagrangian method. So really quick background on this, what we do is take the Lorentz PDE, or we say, okay, if we discretize this in a Lagrangian frame, and we trace the characteristics back in time, and then we use interpolation to figure out what the solution was at the departure points, we can come up with this really neat numerical scheme that's not restricted by typical CFL constraints. Right, and semi-Lagrangian method's pretty old. It was developed back in, I want to say, the late 60s, like the earliest versions of it. So it's been around for a long time, right? And it's super useful, and we like it a lot. Right, and again, the reason we like it is it's unconditionally stable for linear advection. And if done properly, you can resolve fronts, say, for example, level set type interfaces very, very well. Now, the downside is, right, it's a single step method. So if you're advecting something like a level set, you have to reinterpolate the function at every time step. This can result in error. The other problem is there's no inherent mechanism to preserve the incompressibility or conservation or things like this. So it's kind of a very bare bones method. What we want to do is take it and extend it. So what we really want to look at is a way to turn this into kind of a multi-time step method without reducing the accuracy that we have, right? So if you kind of look at this characteristic tracing map, what you can see is the semi-Lagrangian method really applies between two levels, right? So going from Tn to Tn plus 1. And then again, you would apply another semi-Lagrangian method after this. What we want to do is create a map, right, that we can actually expand in order to make this kind of a multi-time level method, right? So the way to do this is to use this idea of a reference map, right? So this is something that comes from the continuum mechanics world, not so much in the fluid side, but you had a group, Cameron, Rycroft, and JC Nave that kind of popularized this maybe about 10 years ago. And the idea here is you construct this characteristic mapping function, this CAC, right? And then instead of solving the original PDE for our scalar field phi, you'll solve an auxiliary advection equation, and then you can reconstruct phi, right, using this map. Now, what we want to do is add some more to this. So you say, okay, we have this map, right, that kind of works in the Lagrangian frame. How could we incorporate this idea of incompressibility? Well, so in a Lorentz frame, we have this divergence-free condition, right? Looking at that in the Lagrangian frame, we say, okay, we have volume preservation. So we want to incorporate this into the actual reference map method, right? And what we can do is take the gradient of our map, right? This actually gives us the deformation of the space, right? And then we take the determinant of this, we can see how volume preserving this mapping is, or what the action of the velocity field is doing to the solution itself. So if we measure the determinant here and it's not equal to 1, we know that our map isn't volume preserving. So the idea for our characteristic bending scheme is to use this, right? And then we design a projection such that we can force the map to be volume preserving. And essentially what this does, if we follow kind of a characteristic of the semi-Lagrangian, right, on this kind of adulterated fields where you have this nice solid body rotation that should be completely volume preserving, you add some artificial compressibility. This will cause the characteristic to start spiraling out instead of staying in a concentric circle. And then essentially what our characteristic bending scheme applies this volume preserving projection to the characteristics. And then what you end up getting is something that looks volume preserving up to whatever order you do the projection for. In our case, we do it to second order. Now we can formalize this algorithm by saying, first, we start with the advection of the reference map, right? We initialize it, we advect this over one time step, we measure the deviation from the volume preserving space, and then solve a Poisson equation to do this volume preserving projection. What that does to the map is cleans it up to within second order, right? And then we can go through and reconstruct the solution, right, using the corrected map. So I've tested this on a bunch of different examples and kind of finalizing a paper for this right now. We look at just advecting Gaussians. We have some solid body rotation examples. We have these really deforming flows, right? And then we look at things that are a little bit more interesting. We have incompressible Euler, right? And we have multi-phase flows. So today, just because we're limited on time, just look at two of them. For the deforming flows, if we compare this to kind of the next best method, which is this volume preserving reference map, this was introduced back in 2021. If we compare this to our augmented reference map with characteristic bending, right, what we see is that for a completely incompressible field, these give you about the same results for both interface error and volume preservation. But when you start adding artificial compressibility to your field, right, the volume preserving reference map doesn't do as well, right? You drop down to first order, whereas our characteristic bending augmented scheme, right, gives you nearly identical results. This is the same for the volume error. You add in this artificial compressibility. The traditional like volume preserving way to do this doesn't work, but our augmented characteristic bending scheme successfully filters out these compressible modes. The other thing that's kind of interesting is to look at the incompressible Euler equation, right? And then the way we set this up is basically we take a manufactured solution, right? We figure out what the gradient of pressure should be, right? And then we turn this into a stationary problem, right? So the velocity field is not going to change. We just integrate everything correctly. And again, we're doing everything here second order. When we do this nonlinear problem with the semi-Lagrangian method, right, what we see is our velocity error is roughly about second order. But the semi-Lagrangian method will diverge from the divergence-free space, right? So if you continually check the divergence of the field, you see that this is starting to drift off. And if you run this for long enough, right, about 2,000 time steps, what you see is the semi-Lagrangian method actually blows up, whereas the characteristic bending schemes, right, these actually remain divergence-free over the long time, right? So it's very cool what we're able to do with this. So to kind of wrap up real quick, characteristic bending is a robust method for doing advection under incompressible flows, right? Because it filters out these compressible modes and it really preserves the divergence-free nature of an initially divergence-free velocity field. So this is really cool. Now, the downside is, right, characteristic bending is more expensive than other methods, right? You're adding a Poisson solve to everything, right? That's not cheap. So you don't want to use this if you do have something that's very, very incompressible already. But if you don't have this, this can definitely help. So kind of as I mentioned earlier, I'm finishing up the paper where we can talk about all of this. We have a couple other papers that kind of hint at why this would be important, where we have one where we're talking just about the multi-phase flows and how you can do this volume preservation to fix things. And then we have some others that talk about the approximate projection method and kind of outlook on why we would want to do some of this type of stuff.
Thank you for letting me to present my research today. My name is Ramin Pahnabi. I'm working with Dr. Shepard for my PhD degree at Brigham Young University. And today I'm going to present on high-order space-time finite element simulation of fluid mechanics using MFEM. As motivations, why we are looking for high performance. Compressible Navier-Stokes is renowned to be complicated due to the nonlinearity and also is present in number of multiphysics problem like tight coupling of fluid behavior and thermal, which comes directly with compressible Navier-Stokes and but frequently interact with chemical process. Our goal is enable robust, accurate simulation of complex, high-speed multiphysics system using a scalable space-time finite element method. The question is how to get high performance in compressible Navier-Stokes simulations. We need scalability, we need efficiency, and also stability. For the scalability purpose, we would like to use the scalable libraries like MFEM, and also for the efficiency, we are looking for maximizing computational speed and minimizing the resource usage. And also for stabilization purpose, we would like to use some stabilization method such as SUPG as a streamline upwind Petrov-Galerkin and GLS for this purpose. This is our goal for getting high performance compressible Navier-Stokes solver that can scale to multiphysics problem. Maybe speaking quickly to the MFEM, as you know, MFEM is a strong framework that supports high performance computing, high order finite elements, and also higher dimensional simulations. Other things, IGA. IGA is powerful for getting high accuracy with fewer elements. As you could see here over the graph, by moving from discontinuous Galerkin to continuous Galerkin to more smooth representation, we can have more accuracy per degree of freedom. This is what we hope to leverage from high accuracy with fewer elements and computational cost. Why space-time finite element methods? finite difference has its own strengths, but we are interested in conservation also. Space-time does have the conservation, but already our two-dimensional problem is complicated, and by adding additional dimension as time, it will be much more complicated. Alternatively, we could use the discontinuous Galerkin in time by having the benefit of the finite difference as time stepping, and also the conservation, the nice conservation properties of the space-time. We could use the discontinuous Galerkin in time and also continuous Galerkin in space. So we would like to use MFEM, IGA, and space-time finite element method in our research. This is the roadmap, what we're going to do. First, we need to have the steady advection diffusion, and after that one, we have the opportunity to go to either to the stabilized advection diffusion or nonlinear compressible flow steady. And similarity, we can have the space-time stabilized advection diffusion and nonlinear stabilized compressible flow steady. And finally, we would like to have our space-time stabilized Navier-Stokes solver. Why we should solve the advection diffusion problem first? As you could see here, the letters are capitalized, but the representation on the left-hand side, which is the advection diffusion, mimics the representation that's given on the right-hand side as a compressible Navier-Stokes problem. And also, we would like to use the variables that are conservative, particularly entropy variable is a good option and choice for our compressible Navier-Stokes problem. And also, for solving the problem, the same as the normal finite element method, multiplying by test functions and taking the integration. And by using the discontinuous Galerkin framework, we could build our block matrix, but here we are solving the problem in 4-dimensional, and our basis function is both in space and time. Again, we are not solving the full 4-dimensional problem. This is 2-dimensional problem and also a bit of additional dimension as a time. Maybe speaking based on the roadmap, we got the expected result with MFEM functionality. This is the results for the steady advection diffusion equation, and also by adding the high velocity without using the GLS stabilization method, we got meaningless and garbage results. And also by using the stabilization method, we got a good results and convergence rates. And also bring us back to the benchmark test or stress test for advection diffusion problem, which is askew to the mesh. We got the bad results, again, without the stabilization method. And also by adding the generalized least square as GLS stabilization method, we got the good results. And this is the added benefit. This is the added benefit to our space-time discontinuous Galerkin framework. And also, this is a video for our askew to the mesh for a space-time solver. As you could see here, you could see some oscillation due to the discontinued behavior, but we are keeping the appropriate boundary conditions and also approaching to STD solutions. I need to mention that we are solving for a very fine mesh in both space and time. And here you could see some challenges that we faced by going from advection diffusion to compressible Navier-Stokes problem. First, it was related to the local form in MFEM. We need to create our local form for compressible Navier-Stokes problem to have 4 unknowns instead of 1 unknowns, which we had in advection diffusion. And also, MFEM provides a strong support for a spatial finite elements method, but for the space-time integration, which is not natively supported with MFEM, there are some branches that can do some of them, but importing and accessing them are challenging. And we decided to manually define our space-time formulation. And another success that we have is related to the boundary conditions. Some of the MFEM functionality for block metrics was not functioning as we expected. and we decided to manually enforce these boundary conditions for our compressible Navier-Stokes problem. This is the path forward. Already we have the nonlinear space-time advection diffusion, and right now we are working on one-dimensional steady shock, and in the next step we will consider higher dimensional steady shock and also adding more geometry, and finally we would like to have our space-time compressible Navier-Stokes that can operate on the complex multiphysics problem. And also here you could see some more challenges that we particularly facing. One of them is related to our solver by switching from multi-character in the paper, Shakib et al., that is not generalized world to more generalized neutral solver. And also for the boundary conditions, some of the MFEM functionality that we expected to work in our examples, that works in examples with MFEM in their own examples, we couldn't use them in a slightly generalized form, and we decided to manually define our boundary conditions that you could see some of them here in our own problem. As a conclusion, by using MFEM, IGA, a space-time finite element method, we would like to develop a multi-physics fluid simulation based on a space-time compressible fluid. Thank you.
Hi, Ramin. Can you hear me?
Yeah, I could.
Oh, I just wanted to say nice presentation. It's always good to see more people who are doing space-time. Everyone's welcome to the club. A few questions for you about your work. So were you doing, was that 1D plus T, 2D plus T, 3D plus T? What was the dimensionality of the problem?
This is, we are solving for the spatial section as a 2D or 3D, and our time dimension is not a full time dimension. It is a bit of, because it will be much more complicated. And now we are considering our time dimension as a small slab as an additional dimension.
Okay. Turned off again. Okay. So is one spatial dimension plus one time dimension?
Yeah. And this is two spatial dimensions.
And then follow-up
one
question on
additional-
that. Were you using quadrilateral or triangular elements in that?
This is a quadrilateral.
Okay. Like a structured quadrilateral mesh that you were using?
Yeah.
Okay. And then could you, just last question, could you follow up and clarify what the benefits of IGA will be for this particular application?
We would like to have IGA for reducing the computational cost with fewer degree of freedom. And because of that, we would like to use IGA, and yeah.
Would love to talk to you offline a little bit about that. All right. Thank you.
So I have a question for Patrick. Patrick, is any of this work available in a branch or somewhere?
Yeah, so that's a good question. I do have a version of the 40 branch. It's not on the GitHub repository as of the current moment because we had to kind of resurrect the 40 dev branch that is currently in the repository to kind of get it more current than what it probably was when it was created. So that's something I can work on in the kind of near futures, getting something that's available to everyone visibility wise. So yeah.
Yeah, I think that will be awesome.
Yeah, it's always cool to see all these applications, enhancements on top of the code, but it's even better to see some of it come back.
Matthew, is everything that you showed also working in 3D? We can't hear you.
Oh, sorry. My microphone was off. Yes, so I do have everything working in 3D, and I have a lot of examples with the multi-phase flow problems. It's just a little bit much to try and cram into a 10-minute talk. But if you're interested, I'm happy to go through it with you.
What about 4D?
I have not tried in 4D. I don't see any reason why it wouldn't work. But I haven't played around with 4D. So maybe there's
Just want to add, I saw some like cool visuals in there that would make for like strong entries into the Viz contest. So, just want to encourage everyone to submit.
Yeah, I'm always amazed, especially with the student talks. There's so many cool pictures that if you just submit it to the Viz contest, what you'll get a good chance.